Hey guys, welcome to your notes for today. Today we're going to be talking about comparing properties of functions. That's going to look a couple different ways because we have a couple different ways that we can represent our functions. Remember that we can represent our functions through a table, a graph, equation, or words. And you can compare two or even more functions. We're going to be comparing two represented in different forms. So let's take a look at this first one. It says, well, first of all, remember that we have words, tables, equations, and graphs that can show the same thing. But here's our first problem. It says a zebra's main predator is a lion. Lions can run at a speed of over 53 feet per second over short distances. So they've just given us the rates of change and the rate of change for a lion in words. The graph on the right shows the speed of a zebra. Okay. It's good to read our problem so that we know what the graph's actually representing. Compare their speeds. Okay. To compare our speeds, we have to compare our rates of change. We know the rate of change for the lion already. That's at 53 feet per second. Well, if that's at 53 feet per second, we need to figure out what the zebras are. So we can find the rate of change of zebra. Let's choose 2 points on the line and let's find our rate of change between them because we can find it by finding the slope. So I'll do 118 minus the 59 all over 2 minus 1. That will give me 59 over 1 or 59 feet per second. So when it says compare them, you can say something that the zebra can travel at a rate of 59 feet per second. Since 59 is bigger than or greater than 53, the speed of the zebra is greater than the speed of the lion. So you can say speed of zebra is greater than lion because got in my graph there. But because well, whatever. 59 is greater than 53. So even though they represented us, those two functions, two different ways, we were able to compare them simply by finding the rate of change of the one with the graph and comparing it to the one that they already gave us. So let's take a look at another example. A certain car has a gas mileage of 22 miles per gallon. The gas mileage of a certain sport utility vehicle, or SUV, is represented by the function shown on the graph. Compare their gas mileage. So they've given us one already in the words. They said that we have a car that has 22 miles per gallon. So now we have an SUV with this graph and we need to compare it. Now, a lot of you are probably saying, why don't I just use this first point, 119? Well, this works for this situation because we're going through the origin, but sometimes you will not be going through the origin. So it's important that you know to do how to find the rate of change is to do our slope formula, y2 minus y1 over x2 minus x1, in order to find that rate of change, because it's not always going to be that first point if there's a y-intercept. That's not 0. So because the SUV has 19 miles per gallon, you could compare these by saying the car has a better gas mileage because you can get more miles per gallon. Because 22 is greater than 19. Or you could say that the SUV has worse gas mileage than the car. I don't really care how you word it as long as you're comparing the two accurately. So this next problem is asking us the function m is equal to 140h, where m is the miles traveled and h hours, represents the distance traveled in the first Japanese high-speed train. The distance traveled of a high-speed train operating today in China is shown in the table. Assume the relationship between the two quantities is linear. Okay. Now it asks us to compare the functions y intercepts and rates of change. So first let's interpret their y-intercepts? Well, at 0 hours, how much distance has either train traveled? Well, since we haven't measured any time yet, they're both going to be 0. So for the y-intercepts, for both of these, both are 0. For our rates of change, or our slope, well, we already know the rate of change of the first graph. It gives us at 140. So we know the speed is 140 miles per hour for our first Japanese high-speed train. That darn graph. So we already have that first function. But now we have this table. So I'm going to have to do 434 minus 217 to try to figure out our constant rate of change. Since we're going up by 1 on the x, let's find out how much we're going up each time on our y. 434 minus 217 gives me, not divided by, 434 minus 217 gives us 217. And 651 minus a 434 gives us 217 again. So it looks like the speed of the train rate, the speed of our modern train in China is 217 miles per hour. So since 217 is greater than 140, we know that our Chinese high-speed train has a greater rate of change in the function representing, we know has a greater rate of change than the function representing the Japanese high-speed train. So the Chinese modern train has a greater rate of change. If you ride each train for 5 hours, how far will you travel on each train? Well, we're going to have to do 140 here times 5 for our first function. So I'll pull up my calculator and I'll do just that, 140 times 5. And we get that we travel 700 miles. Oops. If I extend my graph here, or I find the function 217h, where h is going to be 5, I'm going to be multiplying 217 this time times 5. And I get 1,085 miles. So we'll travel 1,085 miles on the modern Chinese train. So, wonderful. That's that problem. We've answered all the questions it has asked us. So why don't you go ahead and try to solve this one. The number of the new movie store receives can be represented by the function m is equal to 7w plus 2, where m represents the total number of movies and w represents the total number of weeks. The number of games the same store receives is shown in this table. So we have the movies and then we have the games of the same store. Compare the functions y-intercepts and rates of change. And then you need to figure out how many new movies or games the store will have in week 6. So go ahead and take a second, try to solve that, and we'll go ahead and go over it in a second. So for the first part of B here, compare our y-intercepts. I know that our function for movies, we have a y-intercept of 2. However, for games, the y-intercept isn't 2. The y-intercept is 1 because, sorry, let me try to move this thing out of my way. Yeah. The games are y-intercept is equal to 0, because if I keep going down by 3 and my week is at 0, I have 0 games. The store receives, when I'm comparing the rates of change, the store receives 7 movies per week. Because we have 7W. While games, they are only receiving 3 games per week. So they're receiving more movies than games. So the rate of change for movies is greater. Or the rate of change for games is less. Either one is saying the same thing. See how many new movies and games will the store have in week 6. Well, if we plug in 6 for W, we have 6 times 7, which is 42, plus 2. We're going to have 44 movies. However, games, if we extend our graph, or you know that you're going up 3 times each week, multiply it by 3, and we get that we're having 18 new games. So 44 movies, new movies, and 18 new games. And that's basically it, folks. That's all really it takes to compare these two. Let's look at a different version of comparing, though. Instead of doing words in a table, let's look at a graph in words. Angela and Benjamin each have a monthly cell phone bill. Angela's monthly cell phone bill is represented by the function y equals 0.15x plus 49, where x represents the number of minutes and y represents the cost, and Benjamin's monthly cost is shown on the graph. So our first question here is compare the y-intercepts and the rate of change. So what's our y-intercept for Angela's bill? Well, it's 49. So I would say Angela's bill has a y-intercept of 49, and we can see from the graph that Benjamin's has a y-intercept of 60. So Ben has a greater initial cost, or an initial greater fee, you know. But it looks like he's at the very beginning he's been spending more. That is greater than Angela's. And you could throw the numbers in there if you wanted to. The rate of change, we have Angela's rate of change is 15 cents an hour, or a minute. This is an example of one where you can't just go to 1 and go up to find our rate of change. We're actually going to have to use our slope formula, y2 minus y1 over x2 minus x1 to find Ben's. So I'm going to go ahead and do 80 minus 60, because I don't want to mess with 120 and 72. I'm picked this point and this point. Then I'll do 200 minus 0, and I get 20 over 200, or 10 cents. So Ben has a rate of change of 0.10. So the rate of change for Ben's bill is 10 cents per minute, so Angela pays more per minute than Ben. And that's how you interpret that. What will the monthly cost for Angela and Benjamin be for 200 minutes? So we plug 200 in for Angela's equation right here for x. So we have 0.15 times 200 plus 49. And when we calculate that out, we get $79. And when we use the graph, well, at 200, Ben pays $80. So that's what they want us to do. So we just found those two using both our graph and our equation. And that's all it wants you to do. It wants to make sure that you can read the graph and interpret the information you're actually seeing there. So why don't you try this example, and then we'll go ahead and go over it. Mandy and Sarah each have a membership to the gym. Mandy's membership is represented by the function y equals 3x plus 29, where x represents the hours with the trainer and y represents the cost. The cost of Sarah's membership is shown in the graph. Compare the y-intercepts and rates of change. What will the total cost for Mandy and Sarah if they each have 4 hours with the trainer? So to start off, well, I'll give you a second to pause the video and solve it. Alright, you should have enough time to pause the video and solve it. So first off, comparing our y-intercepts. Mandy's y-intercept is 29. That means she has some sort of initial cost of 29, while Sarah's y-intercept is 39. These were at 0.39. So Sarah's membership has a y-intercept of 39, so Sarah has an initial greater cost. So Sarah's initial cost is greater. Because she's spending $10 more at the beginning of the month. The rate of change when we're looking at it, the rate of change of Mandy's, so Mandy's rate of change is just what's in front of our x there. It's just 3. So she's spending $3 per hour, looks like, per hour per trainer. The rate of change for Sarah's, well, if we do 51 minus 39 over a 4 minus 0, well, 51 minus 39 is 12 divided by 4, and we get 3. So Sarah's rate of change is $3 as well. So what will the total cost be for Mandy and Sarah if they each have 4 hours with a trainer? Well, Mandy, if I plug in $4 for this, I have 12 plus 29 gives me $41. However, Sarah, if I look at 4 hours, looks like she's spending $51. So it looks like Sarah's getting kind of the short end of the stick here. She's spending more. It's the same rate of change, so she's always going to be spending more than Mandy. So, I don't know. Sarah should probably switch gyms or trainers at that point. Alright, guys. Hopefully this stuff makes sense to you. Your homework is on Schoology. As always, if you have any questions, please send me an email. Stay safe, and I'll see you all later.